So in the previous video, I introduced you to EDM process, that was electro discharge machining. Over here, we start with the analysis of EDM and find the mathematical formulations for EDM. So let's start with the assumption for the analysis of EDM process. So the first assumption is spark. It is circular heat source and the diameter is 2 into A. Second, it is semi-infinite electrode surface. So we have the electrode and it starts from one end and it goes forever in infinite length. The third is the electrode is insulated except heat source. So there is a small spark gap in which the spark is generated, except all that space, all the other side of that electrode is completely insulated and there is no machining which is happening. Fourth is heat conduction only in depth direction. So this is an one-dimensional assumption. Fifth is heat input rate is constant during discharging time, TD. Sixth is material properties do not change with temperature. Seventh, vaporization of electrode material is neglected. So we are directly taking it only melting and we are ignoring the vaporization part. Let me explain you the third point in detail. The electrode which is insulated except from the heat source, this is because since the electrode is infinite surface and there is fluid also present over there, so the machining should happen at all the place. It will happen by default at all place, but we are saying it is happening only at that small section in which the sparks should be generated. So why the sparks are not generated in other section is because the tool surface, the tool geometry is such that the distance between the tool surface and my job surface is larger, and due to that the ionization field is not enough. The electric field which is generated because of that voltage difference is not enough. When the distance is small, where the machining should be happening, the distance is maintained very small, and that leads to generation of electric field, ionization, and hence machining. So let's start with the modeling process. So here is my surface. This is the Z direction in which the heat transfer is happening. The spark is generated in a cylindrical surface and the diameter is 2a. So r, theta, and z, the cylindrical coordinates are shown over here, and the heat input rate is shown over here in this graph. So heat input rate is some constant for time discharge time. So the governing equation will be the heat equation directly, which we know. Del theta by del t is in terms of alpha, that is heat conductivity, and this complete equation that is in 2 dimension theta, r and z. So we have ignored the theta direction. We are assuming a cylindrical symmetricity. So for the boundary conditions to solve this equation, the t less than equal to 0, my theta is always equal to 0. That is, there is no temperature gradient. Theta indicates the temperature gradient and not the absolute temperature. And for t greater than 0 and outside my cylindrical zone in which the machining is happening, there is no temperature gradient with z direction. So the temperature remains same. And the main conditions come for the cylindrical surface in which a cylindrical boundary in which my machining is happening. So this is the condition: minus k del theta by del z is equal to h upon pi a square td. So h is the heat generated. Now let's, so for t less than equal to 0, my all temperatures are equal, and t greater than 0, but out of the machining zone there is no change in temperature. For t greater than 0 and in workpiece spark region or that cylindrical region, the heat input on surface is equal to heat conduction in z direction. So this is my condition. H is equal to total heat input by spark. So the rate of heat input will be H total minus Hm rho pi a square into z upon pi a square Td, and H total is heat input, total heat input, and Hm is melting heat or the latent heat required for melting operation. So the crater volume Vc will be pi by 6 Hc 3a square plus Hc square into centimeter cube, and Hc is the depth of crater, A is the radius of spark, we already know. Hc is estimated as k1 into w raised to 1 by 3. 2a is equal to k2 that is the diameter, is equal to K2 raised W raised to 1 by 3. W is the power. Power is given by the energy by time. The energy over here is half CV square, that is the capacitance energy. So VC will again be pi by 6 K1 common into 3 by 4 K2 square plus K1 square into W in terms of centimeter cube. But we are not going to use this formula. So let's stop over here. In the next video, we'll look at some relationships and dependency of my Z and machining time or discharge time. Thank you.